Arr! Nothing like the smell of salty pixelated sea spray, the sound of waves crashing against the side of your speaker cones, the feeling of a fish tugging on your mouse cord? Wait, hold on a second. That's not real fishing. That's just a video game fishing minigame. Wait, hold on a second. Okay, much better. I love fishing minigames as much as anyone. I play hours of them in basically any game that has them, and probably my favorite of all time is the one in Stardew Valley. Despite having just one button of input, it feels genuinely skill-based, and it has a really pleasing difficulty curve as you try to catch bigger and better fish, where the hardest ones truly feel like a fight for survival. Except for, you know, the fact that the fight is really just you clicking and unclicking your mouse over and over. Until now! You see this big beefy DC motor? Well, by using the same principle as regenerative braking, I can turn the turning of the handle into a real-world physical replacement for the usual boring movement of your mouse. But I'm getting ahead of myself a bit.
First of all, if you've never played the game, I'll sum it up for you quickly. While fishing, you control the green box that's moving up and down. You want to keep it behind the little fish icon, which moves around randomly. The more valuable fish move faster and more sporadically. You move up by clicking the mouse button, and anytime you're not clicking the mouse, the box will naturally move down. The progress bar on the right side goes up if you're behind the fish, and down when you're not. Filling it up all the way means you win, and letting it fall to zero means game over. So now, let's get to building.
So to start with, first, I needed the fishing rod itself. So I went to Walmart, landed the cheap and home of the save, and got myself the world's finest fishing rod, $9 whole. Next I needed to find a way to mount a motor on it, since the motor is the heart of the project.
So I took off the spool and tried to find a way to connect mechanically to the spinning of the handle.
When I take apart the housing, you can see the mechanism of the reel in action. Well, you can sort of see it anyway. I made this simplified and extremely not physically accurate 3D model to help demonstrate so you can actually see it, and each main moving part is a separate color. Turning the handle of the fishing rod turns this whole blue shaft, which at the same time turns both this little cog and this big bevel cog that's blocking most of the view in the real life video. You can see it here that the small cog meshes with this guy in the back, which interfaces with this block here. The block transforms the rotation of the gears into an up and down linear motion, which I'm guessing is accomplished by something like a simple eccentric cam mechanism, like the one in this video. That moves the post up and down, and that post goes all the way up through the hole in the middle of this worm gear, and we usually push against the spool holder, which lets the reel wind all over the spool instead of bunching up in one place. But the bigger bevel cog on the other side of the shaft meshes with the worm gear, which translates the rotation up and turns the entire reel body, which would normally wind or unwind the spool. Hopefully that makes sense, but if not, the important thing to take away from this is that ideally you would be able to connect a motor to the output of this worm gear, which does the turning of the reel body, so that the turning of the motor and the turning of the handle are directly mechanically linked. The issue is this big post, which goes through the middle of the worm gear, like I said, and gets in the way of everything on top of the reel body. But if we take that bit out, now we have a nice clean space up top where the spool would normally be, and now I can put in this 3D printed motor shaft coupler, which I screwed into place through some holes that I drilled and tapped in the reel body. And now I can mount my motor into place with this massively over-engineered motor mount that looks vaguely like a medieval torture device. And okay, with all that out of the way, the point is that now I can spin the handle and it spins the motor shaft. Wowee! I thought this would take like 2 hours, but instead it took like 2 weeks because my name is Goldilocks. I had to go through a dozen different motors before I found one that had just enough mechanical resistance to feel just right. The things I do for literally no reason since you can't even tell how nice it feels over video. Anyway, now let's move on to how that really works. Originally, I was thinking I would actually send power to the motor and it would basically spin the handle in one direction or the other, either with the direction you're trying to turn it so it would help you turn and make it feel easier, or the opposite way, and then it would feel like it's resisting your turning. But this poses some annoying electrical engineering challenges having to do with something called back EMF. A lot of you probably know this, but there's actually no difference at all between a motor and a generator. In principle, they're literally identical. It's called a motor when you put energy into it to make it spin, and it's called a generator when you spin it to get energy out. I won't go too deep into the details, and different types of motors work differently, but the general principles of how motors work is that you can exchange electricity for magnetism, or vice versa. Because if you make electricity move down some wire, it causes a magnetic field around it, turn into a loop, and not just because of the geometry of the situation, you now have a magnified magnetic push all in one direction through the loop. In the case of this DC motor where you send electricity in, there are a couple of stationary magnets positioned around the side to push against the magnetic field made by a loop, which makes it spin. What's cool though is that you can do the exact opposite, and if you mechanically spin the loop of wire inside of the motor, the magnetic field of the two stationary magnets actually makes electricity flow through the wire, and you get voltage out the other end. That's obviously a super brief and hand-wavy type of explanation, but I'll link a video dedicated to explaining in the description if you're curious on the details. So this voltage that we created inside the rotor loop by turning it through the magnetic field is called an EMF, or electromotive force, and yes, that is the exact same EMF as on those stupid EMF reader things that ghost hunters use. If you ever want to make a quick buck, I've never actually taken one of those things apart because there's absolutely no way I'm spending this ridiculous amount of money on one. But I'd be willing to bet that all these stupid things are just a voltage reader on a loop of wire, and then they upcharge you like 10,000%. Okay, but anyway, the whole point of getting into all this is to say that the back EMF is a bit annoying. Yes, you can really carefully put in diodes to control it, you'll also be sending current into your power source, but this thing costs like $30 on Amazon, so I'm not sure I trust the safety precautions to not burst into flames, and I am unfortunately not an electrical engineer, so I'm not sure that I trust myself not to burst into flames either. There's also the very annoying practical issue, which is that the whole point of this thing is to use it as a controller, and so I want to actually use the motor to read how fast you're spinning the handle at the end of the day. And so in order to get this input into the computer, we either have to somehow figure out how hard you're pushing against the handle or how fast it's spinning or something like that, and then feed that into the computer somehow. Of course, any of you that have worked with motors before know the solution to this is something called an encoder, and I have tons of experience with coders, but like, I kind of hate them. They're really fiddly and annoying to design around if you want one that actually gives you a meaningful resolution. So if there's an easier way, I usually spring for it. Fortunately, while I was doing research on how to safely control the back EMF, I had an idea that lets us catch 2 fish in 1 hook. Or something like that. Instead of using this thing as a motor, we use it as a generator. That not only solves the back EMF problem, but it solves the computer input problem too. Because now we can easily just read that voltage that we made, the back EMF that I was talking about, when you spin the handle, and suddenly you have a perfect signal to use for the game. But at the same time, and this is the really cool part, is it actually gives us a really nifty way to change the force that we feel on the handle. And that's where the regenerative braking thing that I was talking about at the beginning of the video comes in. If you've heard of regenerative braking on cars, it's where you can stop the turning of the car's axle, but instead of powering the motor with the battery, instead you do that exact trick that we were talking about before, and use the motor instead as a generator to push current back into the battery. This basically lets you use up energy stored in the wheels and axle of the car and converts it first into a magnetic field in the motor, then translates it into electrical potential energy in the battery. Again, we're skipping a couple steps here and it's a bit hand wavy, but that's the idea. An important thing to remember is, because of the conservation of energy, you don't get anything for free. All the energy that you're putting into the battery comes out of the kinetic energy that was in the wheels and the axle, and that's what makes them slow down and gives you the braking effect. We can do the exact same thing with our fishing rod setup by just connecting our motor to any complete circuit whatsoever. In fact, the core of my final setup basically just dumps all the energy into the resistor. What we've made here is a big loop of wire, and the mechanical energy of turning the handle, which of course at the end of the day is just turning that loop of wire inside of the motor, is being converted into electricity in our circuit. And like I said, the energy doesn't come for free, and as soon as you complete the circuit with that resistor, the handle gets harder to spin. I set up a very simple circuit to demonstrate this. The 2 wires that you see are the 2 wires coming out of each side of the motor, and one side goes through this resistor over to this MOSFET, while the other side goes to ground. A MOSFET, by the way, is basically just an electrically controlled switch.
I set up a little software simulation to show this. You can see that I send power into this pin of the MOSFET using the button, and when I do, it lets current flow into the LED, which turns it on. As soon as I let go, it turns off. In the real circuit, I use an Arduino to control this instead of a button.
So when I command via this Arduino, the MOSFET closes the circuit, and the 2 sides of the motor meet through the resistor. When the MOSFET isn't getting the signal though, the circuit isn't closed, and so electricity can't flow through, and it's as if you have the wires not connected to anything at all. I have the LED going on, by the way, when the MOSFET's connected, so that you can see when it's on. This works great, and you can really see when the MOSFET kicks in. I promise I'm turning the handle with the exact same force the entire time throughout this video, and you can immediately see that when the LED turns on, I suddenly can't turn the handle nearly as fast. There's one little issue though, which is that it only works in one direction. You can see that in the other direction, when the LED switches on and off, I'm turning the handle at basically the exact same speed. This is a little bit in the electronic engineering weeds, but I think this is because MOSFETs have something built in called a body diode. You can think of this as basically like an electrical valve that's used to protect the MOSFET and the circuit around it. It lets current go in one direction and not the other. In the direction where current can't flow, it's like the circuit's being broken all the time, regardless of what the MOSFET is doing. So in the final circuit, instead of using a MOSFET, I switched it out with a relay, which is a different type of electronic switch, basically does the same thing. And in this case, we're physically moving a piece of metal with an electromagnet to open or close the circuit, more like a real switch on a light switch or something like that. No diodes here. And you can see that as soon as I switch it out, suddenly it works perfectly in both directions. So now we're actually almost entirely done with the circuit. Only just a couple more small details to add. Just having it be hard or easy with 2 levels is fairly cool, but I thought it'd be even better to have a bunch of different levels of difficulty in turning the handle, which we can actually do pretty easily just by having different levels of resistance on the resistors that we connect. The less electrical resistance you have across the motor, the less electricity and magnetism you're creating around the wire, and so the harder it is to turn. This is a little counterintuitive, but actually this means that less electrical resistance means greater physical resistance, and vice versa. Anyway, the important thing to note is that it's really easy and simple to actually add different mechanical resistance levels to the turning of the handle. And in addition to that, my little foray into MOSFET body diodes started out as fixing a bug, but I actually kind of liked how it felt to only have mechanical resistance in one direction, and then as soon as you switch direction, it gets easier or harder again. This gave me the idea that in the circuit, we could actually pass the current through diodes at the end of the circuit after the resistors, and that way we could choose whether or not we want to have that kind of diode action in one direction or the other. So anyway, you can see the final circuit here. I wired up a series of relays with different resistor and diode paths, and then connected the voltage to the Arduino to read, and suddenly we have the full controller working. You know, after many hours of debugging serial communication from Godot to the Arduino, which is of course my favorite pastime. But now I present to you Stardew Valley. Oh wow, look, it's the completely real and unchanged Stardew Valley beach and fishing pier. Just don't pay attention to this incredibly jank animation they had to manually extract from screenshots. Go down here, you can see everybody's favorite Stardew Valley thing, which is the jank bubble animation in the middle of the water. Whoa, it's a fishing minigame! But this time, you can control it with our fishing rod controller. Okay, enough of this dumb gag. Here's the game I've been promising. You can see that it starts out pretty easy, but every time I fill up the bar, it starts a new countdown. I also added in some icons at the top of the screen for what resistor and diode is currently active. And that's obviously not for the game. You can't really tell what's going on, it's going too fast, but it's more for you guys to be able to tell what's going on while I play, since you can't actually feel the resistance in the handle like I can.
I guess I should explain that the way I coded it is that the resistance gets harder the further away from the fish that you are, and the diode direction always points towards the fish. Also, the fish gets faster and more sporadic as you get to the higher levels, while at the same time your bar gets smaller and harder to move.
To spice things up, since there isn't, like the rest of Stardew Valley in the game, I also added a health bar, which is the red bar up top. It goes down if you let the fish progress bar, or whatever you want to call it, empty all the way, instead of giving you a game over instantly like in real Stardew Valley. And the health stays with you as you go through the levels to incentivize you, actually trying in every level of the fish. You can see it's definitely harder here as I go through the levels. I have to say, honestly, this is extremely fun, if I may say so myself. Obviously, the minigame is pretty fun in the original game, just clicking the mouse, but having an actual handle to spin and having that actual physical feedback, being able to feel the fish fighting against you, I guess, if you really want to go there, it's just so satisfying. I keep playing here a bit until I lose, and just to fill time, I'll give my little plug here that if you're still watching the video, I'd really appreciate if you hit that like button.
I'm going to skip forward a little bit, but before we get to the end, I'd just like to say that I have another video just like this planned for the near future, so if you like it, subscribe so you'll get notified when that comes out. Thanks.
Oh, okay, well, there, it looks like I lost and I didn't actually program an end of the game, so it kind of just ends there. Well, anyway, we can close that, I guess. So, I hope you enjoyed. Thanks for sticking around to the end of the video. I really appreciate you, and hope to see you next time. See ya. Bye-bye.